You know, when you look around at towering skyscrapers, massive bridges, or really even just the sidewalk right beneath your feet, it's incredibly easy to dismiss the gray material holding it all together as simple dirt or stone. But in this explainer, we're going to entirely reframe that ubiquitous gray powder. It's not just crushed rock. It's actually a highly advanced, carefully engineered, high-tech code that quite literally builds the foundation of our modern world. Today, we're exploring the fascinating, fiery, and hyper-precise step-by-step process of exactly how cement is made.
Okay, let's dive into this by busting a massive common misconception right off the bat. Have you ever pointed at a sidewalk and called it cement? Honestly, almost everyone does it, using the words cement and concrete interchangeably. But are they actually the same thing?
The short answer? No way. Cement is just the ultra-fine, high-tech binding powder. Concrete, on the other hand, is the final structural product you get when you mix that cement with water and aggregates. You know, stuff like sand and gravel. Think of cement as the flour and concrete as the fully baked, finished cake. Without the high-tech glue of cement, concrete, the actual building material of our cities, simply does not exist. So, our explainer today is going to function a bit like a factory system map, tracking the entire chronological journey of this material. We'll be hitting extraction and raw materials, precision milling, the kiln transformation, cooling and final polish, and lastly, the global scale and future of the industry. Step 1. Extraction and raw materials, the absolute foundation. Before we get into the heavy machinery of the modern process, it really helps to anchor this material in history. Way back around 200 BCE, the Romans created an early concrete by mixing volcanic ash with lime and seawater. They made a material so incredibly durable that structures like the Pantheon are literally still standing today. Fast forward a bit to 1824, and an English bricklayer named Joseph Aspin patents Portland cement, named because it kind of looked like Portland stone, by heating limestone and clay. Today, we've scaled that basic concept up into massively advanced, highly automated manufacturing. And what's wild is that ancient Roman self-healing volcanic ash mix is actually inspiring today's cutting-edge sustainable cement tech.
Now, what's really interesting about this is that after heavy machinery and explosive blasting extract the raw earth from the quarry, the process immediately demands sheer chemical precision. You don't just scoop up random dirt. The finest cement requires a perfectly precise, data-driven chemical ratio to form what's called the raw meal. We need exactly 80% limestone to provide critical calcium carbonate and 20% clay and other additives for the silica, alumina, and iron. It is a highly controlled recipe right from the jump.
Section 2. Precision milling. We're going from megatons all the way down to micrometers.
So how do we physically break down those massive boulders from the quarry? It happens in 3 distinct steps. First up, primary jaw crushers take the large limestone rocks and aggressively chew them up. Second, secondary cone crushers reduce that size even further. And finally, the material drops into vertical roller mills to be ground into a superfine powder. Actually, modern vertical roller mills are an incredible feat of engineering all on their own. They save about 30% in electrical power consumption compared to the old-school rotating ball mills, a real game-changer for efficiency.
Section 3. The kiln. The inferno of chemical transformation.
Now we hit the absolute climax of the process. That fine, raw meal powder gets swept into a massive, slowly spinning rotary kiln. Picture a giant metal cylinder up to 200 meters long and 6 meters across. Inside, the environment essentially mimics the heart of a volcano, reaching an unimaginable 1450 degrees Celsius. That's over 2600 degrees Fahrenheit. This intense, roaring heat is the absolute core of the entire operation. So the crucial point is understanding what this extreme heat actually does to the stone. It triggers a complex chemical reaction known as calcination. As that powdered rock travels through the kiln, the intense heat fundamentally alters its molecular structure. It literally decomposes the limestone, forcing it to release carbon dioxide gases and leaves behind pure calcium oxide, which we call lime. At the very peak of this 1,450-degree heat, the materials partially melt and fuse together. The fine powder transforms into these hard, marble-sized nodules known as clinker. Clinker contains the vital calcium silicates and aluminates that give cement its incredible binding properties. It's the essential intermediate form of cement born right out of that inferno. Moving into Section 4, cooling and final polish, engineering the powder.
As that red-hot clinker drops out of the kiln, a massive grate cooler uses rapid blasts of air to drop its temperature from 1450 degrees down to roughly 100 degrees Celsius in just 20 minutes. This flash cooling preserves its optimal crystal structure. Once cooled, it enters the final grinding mills. And this brilliantly illustrates a key piece of the puzzle. Here, we absolutely must add exactly 3 to 5% of a mineral called gypsum. Without that gypsum, the delicate chemistry of construction would completely fail. The cement would harden almost instantly, the exact second it touched water on a job site. We'd never be able to work with it. Additional ingredients like fly ash or slag are also often blended in here to enhance the concrete's durability and shrink its overall carbon footprint.
But wait, before any of this newly engineered gray powder is bagged up or loaded into giant transport silos, it undergoes some serious scrutiny. Fully equipped physical and chemical labs are continuously testing the material. In a modern plant, these labs are analyzing over 140 samples a day across 11 different sampling stations. This continuous high-tech testing guarantees the powder meets absolutely exacting global performance standards.
Finally, Section 5, Global Scale and Future. Building tomorrow. Let's move to the macro scale and see how this actually builds our global economy. The physical and financial scale of the cement industry is just mind-blowing. Annually, the world produces over 4 billion tons of cement, with countries like China and India leading the output. This production drives a massive global concrete industry valued at over $600 billion. I mean, it is literally the most widely used man-made material on the planet. However, creating the foundation of the modern world carries a heavy environmental cost. Because of the massive amounts of fossil fuels required to heat those kilns to 1450 degrees, combined with the carbon dioxide inherently released during the calcination of the limestone, cement production alone accounts for a staggering 8% of all global CO2 emissions.
Now, the industry completely recognizes this immense challenge, and they are racing to innovate. Cutting-edge sustainable technologies are currently being developed to balance our huge need for cement with its environmental impact. This includes installing advanced carbon capture tech directly at the exhaust of the kilns, developing new low-emission geopolymer cements, and, like we touched on earlier, engineering that Roman-inspired self-healing concrete. Concrete that repairs its own cracks means we have to pour and replace it far less often.
From raw earth blasted out of a quarry to an inferno that completely changes the molecular structure of stone, to the ultra-fine, high-tech gray powder that builds our bridges, skyscrapers, and homes, the step-by-step journey of cement is an absolute masterclass in human engineering. But as our cities continue to grow, our methods really must evolve. So the next time you walk down a sidewalk, look down and ask yourself, how will we engineer a greener foundation for tomorrow?